All right. Happy Wednesday, guys. How are we doing today? Doing good. Can I get some thumbs up, thumbs sideways, maybe some thumbs down? All right. Anyone got anything exciting going on this Thanksgiving break? Yeah.
We're gonna go to Sky Zone with some friends.
What is it?
Sky Zone with some friends.
Oh, Sky Zone. Cool. Anyone else got anything exciting going on that want to share? Yeah.
I'm probably going to have an entire Thanksgiving party with my extended family.
Cool. Is that gonna be at your house?
No, it's really too small.
Oh. Anything else? Yeah. What's up? What is it? Trabajo? Oh, you have work? Oh. Is that very exciting or is that very boring? All right. Well, excited for that. So today, as Mr. Zook said, we're going to be talking about friction. But first, if someone wants to give me a reminder, who remembers what Newton's first law is? Does anyone remember what Newton's first law is? Yeah.
No change in velocity without unbalanced force.
No change in velocity without unbalanced force. Is there another way we can word that? There's another way that we tend to use that before. I think a more common way that it's typically talked about is an object in motion stays in motion and an object at rest stays at rest. That's right. So, going with that logic, if I were to take a brick like this and slide it on the table, it should slide forever, right? Yes?
No.
If I just slid it on the table, it's gonna go forever? Why?
Friction.
Because of friction. What about a ball? If I slide a ball on a table, will it go on forever?
No.
Why not? Because friction as well. Does friction still happen in a ball that's rolling?
Yeah.
Yeah. So that's true. Friction does happen on a ball that's rolling, but rotational friction is a little bit different from sliding friction. So we're not going to talk about rotational friction today. We're just going to focus on sliding friction. So, as you can see here, we've got a diagram going on, and talking about friction, which is a force that always opposes a sliding motion between two surfaces. So when two surfaces are sliding together, friction is going to be applied depending on kind of what the material is made of. We'll talk about how that changes what the friction is going to look like. And the amount of friction or force depends on the surfaces and the force pushing them together. So what we're going to do is, well, first, what I want to talk about is Mr. Zook tells me that you guys were working on some experiments yesterday with shoes and weights, and you were pulling some stuff and measuring some things, right? So what was the general trend that you found when you added more weight to your shoe? It's harder to pull. So the more weight that you added, what would you say increased? The force needed to pull in the friction, right? Yeah. Okay. So I understand that some of your graphs look a little bit different depending on kind of where you place the weights on your shoe, because sometimes it was a little bit unbalanced, but generally your graphs kind of showed a linear progression where the more weight that you added, the more pull force you needed to move the shoe, right? So these two things are directly proportional. So knowing that, what I want you guys to do is get into groups. You're gonna grab a whiteboard and we're just gonna work on this free body diagram where you're gonna draw me all the forces that are supposed to be applying on this brick while it's being pulled in this direction at a constant rate. So get in groups, grab a whiteboard. I'm gonna trust you guys to get in responsible groups and kind of try to make it happen.
Fewer than 10 people per group, all right?
Yeah. I did make sure I know how drawing on this thing works.
So yeah,
I go here,
pick between
different colors.
and then highlighter. It's the Mac window, but this is just direct wire now to here. So it's,
Yeah.
internet goes down, this will still work.
Nice.
I'll get out of the way so you can use it a little bit more freely.
That guy's right there.
And then this is working as well. Yes, cool.
If you guys need more erasers,
Awesome.
grab a paper towel. That's fine.
How much time? 5 minutes.
Perfect.
If a pen's dead, just throw it away, please. Don't put it away.
Let's. Nice.
I'm gonna make more erasers out of the old towels.
Oh no, will we do the dot thing?
Yeah, no.
We'll do the dot thing.
Can I read
I think you know the count. You're used to the back count. Oh, that's
Yeah.
the A to Z. That is that count. We just said, yeah, that count. Alright, we gotta draw the full source. So we got.
But this is gonna be a fun.
Oh, yeah.
This is gonna be more.
I mean, technically, the front force is
I used to see them, but I saw KY on me.
Dude, my signature looks like a blue scribbled up.
That's all signatures.
maybe like.
All signatures.
Maybe just like which one.
Yeah,
Don't raise your hands.
Is it pushing or
it's pushing.
Oh,
That was intended to be a
Big
rope
bolts.
attached to like a knot thing, like the wood blocks.
Oh, so it's
cool.
yeah. I mean, because friction is always pull. I'm just saying. If we're talking about friction.
Yeah, it's pulling it.
I'm just saying the apartment was pulled.
you got those
Alright, I think we all got something written down. Let's go in order, starting over here. What you guys got? What forces you have?
force neutral, force of friction, force of gravity, and force of pull.
Alright, so you said force of neutral. Where's that one going?
Force up.
That one's going up. And then what else?
Force of gravity going down.
Force of gravity, a different color, going down. And then,
Force of
are these two, is one of these stronger than the other,
no,
or
neutral.
they're neutral? Yeah, at a neutral state. Okay. What else?
Force of friction going to the left.
Force of friction going. So this is pulling this way. So force of friction going this way, right?
Yeah.
Cool. And then anything else?
Force going to the right bigger than the arrow for the force of friction.
And then this one's bigger. And then this is E force. All right. That look about what you guys got?
Yeah.
All right. We got the same thing over here. Cool. How about you guys? Same thing? Same deal? Same deal over here. Everyone's pretty much look about like this? All right. Sweet. Guys get full points. 1 million points for everybody. Yeah. So that is correct. Our weight of the object puts force on the surfaces and increases the resistance to slipping. So this is the equation that we're going to be working with to kind of figure out how the pulling force works. It's pretty simple. Importantly to note is that the force of friction is going to be equal to the coefficient of friction, and don't worry about this little symbol. This is just the Greek letter for mu. Greek letter, so you can just kind of write it like that. You've seen plenty of Greek letters in this class before. And importantly, it's going to be that, which is the coefficient of friction, times the force of the normal force. And we want to make the distinction that it is the normal force and not the force of gravity that you're multiplying by. Of course, pretty much everything that you're going to be working with is in a neutral state, so they're going to equal the same thing. The force of friction is pretty much always going to be equal to the force of gravity. But it is an important distinction nonetheless. How much time do we got going here? We can work a little bit more. So now in your notes, we're going to start working on, oh, yeah, no worries. I'll keep this up here. Take your time. Give me a thumbs up, thumbs when you guys are all good. Oh, whoops. I did do the force of friction. That is not correct. It is the neutral force. I said the right thing, I just wrote down the wrong thing. Alright, are we all good?
Yeah.
We got this section down? No? One more minute. Okay, cool.
The bottom with the red, is that force neutral? Equals force of gravity? Or your cursor is?
Yeah, that's force neutral. Everyone good? Sweet. All right. So we'll give this problem a try. If we have a box that has a mass of 30 kilograms, what is the normal force exerted on it by the floor? And then B, if the coefficient of friction between the box and the floor is 0.45, how much friction will the box experience in a slide? In other words, when it's being pulled across the surface. So go ahead and get started on that. While you do that, I think I'll start by just reiterating the forces that we are applying here. So we've got force of gravity. We've got normal force. Pulling force, and then the force of friction. Let's go with smaller. So, get started here. Who can tell me how we find the normal force? What is it equal to? Force of gravity, right? And how do we find the force of gravity? Mass times. So normal force equal to force of gravity, and the force of gravity is going to be equal to, should be a lowercase, and looks like uppercase. The mass times the gravity. What's the mass? 30. And what's gravity going to be? Negative 10. Oh, are we use 10 in this?
Use 10.
Okay, yeah.
Is it negative now?
Well, this is, well, it is pushing down, but in this scenario, because it's in equilibrium and we're using the normal force as well, what's it going to be in this case? Positive. In this case, it's going to be positive because we're going to be using the normal force and everything's balanced. So we're going to go positive 10 meters per second squared. And if we plug this into a calculator, this is pretty easy. You don't even need a calculator for this one. What do we get? 300 newtons. So that's going to be the answer to A. And then for B, we have the force of friction is equal to the coefficient, which is 0.45 times what we found, which was 300. And what's that going to give us? 135 units? Newtons. There we go. Pretty easy, right?
Yeah.
This is not. Make sense to you guys? And then if we were to increase the amount of mass that the object we have or are using, what's going to also increase in this case, in answer? Is the friction going to go, the force of friction going to go up or down? Going to go up. Same with what happened when you guys did your shoe experiment, where as the mass increased, so did the force required to pull it. So that's kind of how everything connects. As you increase the mass, the force required to overcome friction is going to be greater, which means the friction is always going to be greater as well. All right, that's about it for me. I'll let Mr. Zook take over for the rest of the questions. Thanks guys for letting me do a little bit of lecture here. Appreciate it.